Okay, I'm going to derive the equations of uniformly accelerated motion using calculus. Now it's in your text. I think you've seen a lot of it if you've done the assignments, but a little synopsis isn't going to hurt. So, we know that the derivative of velocity is acceleration. The derivative of position is velocity. Derivative of the position function is a velocity function. The derivative of the velocity function is the acceleration function. Okay. Now I'm using subscripts. I'm using Vx and Ax for acceleration in the x direction. This is because right now we're actually in the course into motion in 2 dimensions, and the fact that we have x and y components becomes important. So I'm going to use the subscripts, although if you're doing this strictly in 1 dimension, you can leave the subscripts off. Okay? So, anyhow, if our x acceleration is constant, then that means what? Well, that means that the derivative of your velocity function is constant. And if we call the constant a sub x, then we get v sub x prime equal a sub x being a constant number, or constant quantity. Well, what function has a derivative that's equal to a sub x? The general function that has derivative equal to a sub x should be obvious, and if it isn't, then you probably need to think about first semester calculus a little more. It's a sub x times t plus a constant. Now, the integration constants, we're going to call that C1 because we're going to have to do another integration, and we're going to get another integration constant when we find x. Okay, so anyhow, it should be obvious that if the derivative of a function is equal to ax, which is constant, then that function has to be axt plus some constant that we call C1. Then x prime of t equals vx of t. So if vx of t equals this, that means x prime of t equals this. It equals vx of t, which is axt plus c1. So what has derivative axt plus c1? The most general function that has that derivative is very easy. It's 1/2 axt squared plus c1t plus c2. Well, it follows from this that anything that accelerates at a constant rate has vx of t equal axt plus c1, where c1 could be any number. It depends on the circumstances. And x of t is 1/2 axt squared plus c1t plus c2. Now these are actually our kinematic equations, but we want to give c1 and c2 meaningful names. Well, if v of t equals this, then v of 0 is a sub x times 0 plus c1, which is just c1, because anything times 0 is 0. I mean, it's obvious if you let t equal 0 that this goes away and you just end up with c1. But writing it out completely in case somebody needs to see it that way, we see here. If we call v0, and I'm using x subscripts, it should be vx0. If we call vx0 by the name v sub 0x, then v of t equals axt plus v0x. Because v0x equals c1, vx of 0 is c1, and if we call that v0x, then v0x equals vx of 0, and that equals c1, so c1 is v0x. And that's your velocity at t equals 0. Again, so here's an equation. This is the t equals 0 velocity. Then x of t is all this, well, except of course instead of c1 now we've got v0x there, plus C2. Well, if x of 0 equals C2, so we call this x sub 0, and we get this equation here, just replacing C2 by x sub 0. So, check it out. If we plug in t equals 0, this is 0 and this is 0, we get x sub 0. Okay? Anyway, I thought I'd written down both of the equations, but let me emphasize them by circling them, preferably in red if I can find my red chalk. I need to keep these damp rags over here. Okay, so we have this equation, and this equation. We can also eliminate t. We can solve this equation for t and plug the result into this equation. And simplify it and rearrange it to get vx squared equals v0x squared plus 2ax times x minus x naught, where x is your position at whatever time you're talking about, and vx is your velocity at that time. Then we could eliminate ax from the original two equations to get this. And this has a very simple interpretation. Vx plus v0x over 2 is the average of your initial and final velocities, of your velocity, your initial velocity and whatever velocity you have. Since velocity, if acceleration is uniform, since velocity then is a linear function of time, the average of these two quantities is your average velocity, and you see that the displacement from x naught to x during this time is equal to the average velocity times that amount of time. Okay, now I started to write something else and didn't realize I didn't have nearly enough room, so I went over to another board. Okay, with the equations that I wrote that I no longer have visible and I don't have room to move this over and see them, but if you have written them down you can see how this works out. If delta x is x minus x naught, and that makes sense, that's a displacement from position x naught to position x, so that's your change in x, your change in your position. Then we can write these things in a little more compact form. We have delta x then is 1/2 ax t squared plus v naught t vx v naught x t plus I wrote that wrong. That made no sense. Apparently writing symbols without thinking, so I'm kind of discouraged. A sub x t plus v naught x. And let's see if I wrote it right over here. I almost certainly would have, yeah. Okay, I wrote it down carelessly here. Then vx squared equals v naught x plus 2ax delta x. And delta x equals your average velocity v plus vx plus v naught x over 2 multiplied by t, with a note that this is just average velocity times your time interval. Delta x is your displacement. And this equation could have been obvious from the very beginning. Okay, but we did obtain it. We can obtain it by eliminating variables, as I mentioned. Well, this gives us 4 equations with 5 variables: t, v naught x, vx, delta x, and ax. That's all you see in these equations. the way the equations are set up, the way equations are arranged, if you know any three of these, and you can check this out, and you should, pick any three. There are 10 possible combinations of three of these, okay? T V naught Vx, T V naught x, delta x, T V naught x, Ax, T Vx, delta x, T Vx, Ax, V naught x, Vx, delta x, V naught x, Vx, Ax, and Vx, delta x, Ax. That's 10 of them. 10 of them, yeah, that's 10. I can't open this hand. Got chalk in it. Okay, 5 variables. If you pick any one of the 10 possible combinations of 3, you have an equation over here that has those 3. Now, each equation contains only 4 of these variables, which means that whatever equation you get, and sometimes there's more than one, for the 3 that you choose, for the combination of 3 variables that you choose, it's only going to contain 4 variables, so you can solve for the 4th variable. Well then, you know 4 variables. Well, that leaves one that you don't know. Pick any equation that has that variable in it, you have choices, and solve for that variable. There you have it. If you can determine 3 of these quantities from the information you have, you can find the other 2. You also have, of course, the functional relationships for velocity and position. This and this. So you can always, if you know enough, set up your v of t and your x of t. And look at the graph of v of t, look at the graphs of x of t. V of t is always going to have a straight line graph, x of t is always going to be a parabola. Maybe opening upward, maybe opening downward. So there you have it. That's the entire theory of uniformly accelerated motion in a fairly small nutshell. Now, applying it and recognizing what you have and setting up various situations, well, that's why you do problems. That's why you do some guided problems. That's why you do some independent problems. So there we have it.